Good morning, everyone. My name is Adam Butler. I'm Director of Mission Assurance for Wakefield-Vette in the Embedded Division. And I'd like to talk to you a little bit about additive manufacturing or 3D printing, specifically for, in this application, Vita 48. So a quick little overview, how it works. We're going to talk about the process. We'll talk a little bit about the materials that make up the different powders and really the advantages of some versus others. We'll talk about combining additive manufacturing with subtractive manufacturing. And then we're going to look at applying that technology to AFT applications as well as LFT applications. So what is LFT and AFT? Some of you may be familiar with this, but for those of you that are not, it's been talked about as how to apply advanced cooling techniques to traditional VME or VPX cards. So Vita 48.4 in this case is liquid flow through. I'll talk about it as LFT. And Vita 48.8 is referred to as air flow through or AFT. So my friends at Mercury allowed me the use of this slide, and I think it does a good job of showing some of the different form factors that we're going to be talking about. So here we have a traditional like air-cooled card, and we see the technology progression. I know that Mercury did a good job of talking about that earlier. But we're going to focus on mostly today is the LFT applications here, liquid flow through. So this is a full up chassis, a couple different cards. You're all probably pretty familiar with the form factors here. So how does 3D printing with metal work? A lot of people think of 3D printing with plastics. It's pretty common. A lot of people maybe even have a 3D printer at home. I know my kids have a little pin that feeds some plastic material, it heats it up, and you build whatever you want to create. The technology has come a long, long way. Obviously in the plastics industry, there's some incredible things that can be done with 3D printing. But with metal, it's a little bit different. I want to talk about the process here. We have a kind of a progression of how it works. So you have a powder bed that's situated on a metal plate. And what will happen is a laser will come over in this image here and will essentially burn in a predetermined pattern, and you're going to fuse the powders together. That plate is going to lower, a new powder layer is going to come across, and you're going to repeat the process and repeat the process. So what you're left with is a part that is essentially encased in powder, if I can get this to work, excuse me, here. And we then will remove that powder, and you're left with the part that you're trying to create. So that piece of the laser sintering process is very important for LFT applications because you need to remove that powder from maybe an internal liquid channel or whatever else you're trying to accomplish. Even in an AFT application, you can have trapped powder somewhere. So the technology has really changed in the last couple of years to allow this to be possible. Obviously, FOD is the enemy here, so now we have an opportunity to do what we are trying to accomplish. So a couple of advantages to additive manufacturing when it comes to Vita 48. This is a long list, I'm not going to read the whole thing, but the things people think about with 3D printing is typically geometric freedom. You don't have to be constrained by what can you create by removing material from a solid. You can build that into whatever you want. So significantly complex shapes are possible. Some examples here on the right. Something that would be extremely difficult to make either with a CNC application or EDM or whatever you can think of. Hidden or internal features. So we talked about liquid channels for LFT Vita 48.4. It's possible here. Huge lead time and cost advantage over brazing. Right now that is the key technology for building an LFT module. Weight savings are possible. We're going to talk a little bit more about that in my presentation later. We do have a quick example here in the bottom right of the slide where what you would typically see in a lever application as a solid piece can be made with honeycomb structures inside, dramatically reducing the mass inside that object and the weight as well. Simplified assemblies. Some things, and again, additive manufacturing can be applied to numerous different technologies, but when we look at AFT modules today, the typical process is to manufacture at least 3 separate components and to fuse those together either through a braze process or a thermal bonding process. With additive, you can print the whole thing as one piece. So this fun eye chart here, I won't ask you to try to read it because I know it's hard to see, but this is a comparison of different aluminum metal powders that were created to replace 6061 in the market. What this chart is trying to show is that there are different trade-offs with each of those materials. Some may be print speed, some may be strength, elongation, thermal conductivity, which we're going to focus in on a little bit more here in a second. But there are many ways to solve the problem, so you have to then choose which of these materials is best for your application. So again, bringing the conversation back to Vita 48.4, we have arrived on a material called ALSI 10mg as the optimum material for this application. The key differences here when we look at ALSI 10 versus more traditional materials that we see in the industry, such as 6061, 6101, 6063. Most people familiar with metals or in the thermal world will know, the different aluminums have better thermal characteristics. Well, right off the bat, we can see that the ALSI 10 in a stress relief state is right at a 6061 as right off the machine, basically. So I have another example of 6061 RAM 2, which is up here, but I wanted to put this in here while we're seeing not as good as thermal characteristics. This is one of the original powders that was developed for aluminum printing, but the problem with it is it's extremely hard to machine afterwards. So how do we get to where we want to go with additive? Here we have an example of, this is not a customer specific product for IP reasons, but we have a cutaway of an LFT module. So we can see the liquid channels flowing through. You cannot get a fully compliant LFT module with additive alone. While additive is capable of printing at plus or minus 5 thousandths of tolerance, which is, good enough usually in the machining world, you see a surface finish of around 200, which, if you know anything about thermals, is not really good. So we need to then bring that part into a CNC machine and apply the lessons we've learned via subtractive manufacturing to, let's use the word, clean up some of the surface finishes. Tapped holes, the port openings for an LFT specifically are very critical in this application. Any leaks, nobody's going to want leaking jet fuel on their aircraft. Here we also have kind of a cutaway of an AFT on the right side of the screen. Again, what I was talking about earlier is this is typically done in 3 different applications or 3 different components fused together. But in order to get there with additive, same thing. We're going to want to come back in, apply what we know with subtractive, and get a more compliant product for the industry today. So looking ahead, we can take the lessons we've learned at the module level and apply them to the chassis level. So again, here's another example, non-customer IP specific, of an LFT cold wall, theoretical. You can have your liquid paths going in whatever direction you want. If you wanted to have multiple layers of cooling paths, that is possible with additive, something that would be extremely difficult to do with a vacuum braze or a dip braze application. I have some examples of some honeycomb structures here. We can apply what we talked about earlier with weight savings. I know in a lot of these aircraft applications, I forget the name of the presentation, but a pound is worth so much in aerospace. If we can take a traditional brazed chassis that usually weighs quite a lot by the time you get all that metal in there, essentially hollow out the inside of it by creating honeycomb structures inside of those dense walls, you've greatly reduced the mass of that product. So maybe that's good use for additional computing power like we talked about, or maybe that allows them to carry more fuel on the plane. So this is my final slide, and I want to talk about how do you get there from where we are today. So we have successfully printed LFT modules, and we've done that through a process called MFAM, or modifying for additive manufacturing. So that's exactly what it sounds like. You have an existing part. You may require some slight modifications to be able to print it, but then come back into either a CNC machine or an EDM process, remove some additional material, and basically get something that looks and feels exactly like it would if you went through a vacuum brace process. But if you really want to optimize and take advantage of what the technology can offer, you can go through some simulation for additive manufacturing or design specifically from the ground up for additive manufacturing from the beginning. And this is where things get really, really interesting. Again, I have some pictures here of some of the various things that we've talked about, but the optimization opportunities when you throw the rule book out on subtractive manufacturing and say, what can I really do internally to a part to optimize airflow or liquid flow or heat thermal transfer paths, you name it really. It's the challenges to the industry at large, like what problems do you need to solve, and is additive the right approach? And we're all familiar with different engineering techniques to see about fatigue analysis or heat transfer, but when you start really changing the game of what you can get in the end result, it's quite staggering. Within that process, if cost is your main driver, which in a lot of cases, the customers that come to us, it can be, you can change the parameters of the printing. You can even have opportunities to look at, well, hey, I'm not ultra critical of this part of the end result, so we can have that printed faster and maybe a less resolution. But hey, this area is very, very critical to my mission, so I need to focus on that, and the rest of it can be that way. If it's weight savings, we talked about how we can apply honeycomb structures to that. And if what you're after is something that just matches what you can get today through the braze industry, we can do that as well, but at typically a third to half the lead time of brazing. So it's very, very interesting, and I think it's the future of a lot of these products, particularly in Vita 48, because the challenges that are presented are very unique. We have some really high density stuff coming out that needs a lot of cooling power, and the industry does not like a 32 or 48 or 56 week lead time. So I believe that this is the solution, and thank you for your time. Any questions?